Okay, so if no any questions, so let's go to our sixth talk. It's by Sapir, currently pursuing her MSc in electrical engineering at Tel Aviv University, with a focus on detection for autonomous driving. Alongside her studies, Sapir works as an algorithm engineer at Samsung. There she specializes in image processing. Sapir has a BSc in physics and electrical engineering also, and her master's is supervised by Professor Ben Zion and Roy Orfeg. And today Sapir will present on enhancing curved lane detection with deep matching processes. So, welcome.
Okay, so hi everyone. My name is Sapir Kontente, and it's truly an honor to stand here today with you. I'm a master's student at Tel Aviv University, and I really had the privilege of working together with Professor Ben Zion Bobrovsky and Roy Orfeg. Today, I'm excited to share with you our research, CLRMatchNet. Thank you. So today, I'm excited to share with you our research, CLRMatchNet, and tell you how we are improving curved lane detection using deep matching process. So today, we are going to talk about lane detection, and the goal of lane detection is to accurately detect driving lane boundaries for an input image and output a set of points that indicate the position of the lane. Lane detection is an important component for driver assistance systems as it provides crucial information for navigation and safety. But while these systems are so important to our safety, they are far from being perfect, especially when we test them on curved lanes. So let's take, for example, the CLRNet model, which is the top-rated model for lane detection on the Koolane dataset. So when we look at its results for normal scenarios with straight lanes, we can see that it is capable of achieving impressive results of 93% accuracy. But when it comes to curved lane detection, the model's performance drops to 75% accuracy only. So our main goal in this research is to improve the curved lane detection capabilities. In our research, we relied on the Koolane dataset, which is the benchmark dataset for lane detection, and it includes 9 categories. 8 of them are challenging ones, such as night, shadow, or dazzling scenarios, and we're going to concentrate on the curved lane section. So I'm very excited to share with you that our research has led to almost 3% improvement in the curved lane section on all 3 backbones that we tested on, and we're capable of maintaining consistent results across all other sections of the Koolane dataset. To explain our solution, we'll start by introducing the CLRNet model, which is the state-of-the-art NCORE-based model for lane detection that we used as the basis for our approach. So let's take, for example, the following image, and suppose that we would like to detect the yellow lane with the CLRNet model. So for that, they're using a backbone to extract features from the images. These features are then pulled by the predefined straight lanes NCOREs to generate an NCORE feature map for each NCORE. These features then proceed through another model that output multiple prediction candidates that can be seen here in blue. And the next step is called the label assignment process, which is responsible for filtering from all the blue predictions only the ones that best aligned with the ground truth, which can be indicated here in green. Only those predictions are then continued to the loss function as part of the training process. So our main contribution in this research is in improving the label assignment process, and therefore we will dive deeply into that section. So the label assignment process is a common step in NCORE-based models, and it is responsible for labeling predictions as positives or negatives based on their alignment with the ground truth. Usually, this process relies on cost functions that give a score for each prediction and ground truth pair based on geometrical and classification attributes. Let's take, for example, the CLRMatchNet model, and we can see that the cost function in this model includes two terms. The first one is the geometrical term, and it consists of the relative distance between the prediction and the ground truth plane, the relative distance between their starting points, and the relative distance between their end goals. All those components are then multiplied by each other, squared, and multiplied by a factor. Here, the factor is -3. The second term is the classification score, and it includes both the positive and the negative components of the focal loss. All those components are then summed up to give a score for each prediction and ground truth pair. The problem is that these cost functions are heuristic functions, and they are low-dimensional and have limitations, especially in challenging scenarios such as curved lanes. So in our solution, we wanted to answer two main questions. The first one is, what is the optimal combination between all those components? What should be the factors? Should we multiply them all? Should we sum them up? The second question is this function optimal for curved lanes as it is optimal for straight ones? So in our solution, we would like to introduce MatchNet, a deep learning sub-module for labeling assignment process that we developed to replace the classical cost function and to use the same attributes that were used in that cost function to give a score for each prediction and ground truth pair. MatchNet includes 4 fully connected layers with activations between them, and it is trained offline. To train MatchNet, we are using a teacher-student setup, where the teacher is a pre-trained CLRMatchNet model, where you can see it here in gray blocks. And the student is MatchNet, which you can see here in blue blocks. So whilst the CLRMatchNet model is training, it provides both the inputs and the ground truth estimation for training MatchNet. So we're training the CLRMatchNet model, and while it is training, it outputs for each image multiple prediction candidates, and it calculates for each one of them the geometrical and classification attributes. It also gives a cost score and a loss score for each one of the pairs. And we're taking all this data and use it to train MatchNet. So we take the geometrical and classification attributes and use it as an input for MatchNet. And we take the cost score and the loss score, combine them together to generate the ground truth for training MatchNet. So let's look at some examples for the labeling assignment process by 2 methods. So here in red, you can see the results for the labeling assignment process of the original model CLRMatchNet, which relies on the classical cost function. And here you can see the results in blue for our network, MatchNet, the deep learning module for labeling assignment process. And we can see that we are capable of detecting curved lanes that better align with the green ground truth than the ones that were detected by the original model. On the right side, you can see another example for that, where we have better detections than the original model. Okay, so the final solution, we used the CLRMatchNet model as the basis for our approach, and we replaced the cost function with MatchNet, the deep learning module for labeling assignment process, and therefore the final solution is called CLRMatchNet. So let's take a look at some results. On the left side, you can see the results of the original model, CLRMatchNet, and only the lanes that were colored in blue were successfully detected by the model. And on the right side, you can see our results for CLRMatchNet. And we can see that we are capable of detecting much more curved lanes than were detected by the original model. We also have better detections in hard scenarios. Here you can see an example for detecting lanes in the night or where there's shadow. Okay, so our main contributions are as follows. we introduced MatchNet, a deep learning submodule for labeling assignment process. MatchNet replaces the classical cost function and improves the label assignment process for curve lanes. And our final solution, CLRMatchNet, has led to almost 3% improvement in the curve lane section. For additional information, please refer to our paper and code. Thank you for listening.